Hello and welcome to this session on statistics. In this session, we are going to discuss about ANOVA test. ANOVA stands for Analysis of Variance. So, analysis of variance is a method for testing the hypothesis that there is no difference between two or more population mean. So, ANOVA is a procedure for testing the difference among different groups of data for homogeneity. So ANOVA test allows a comparison of more than two groups at the same time to determine whether a relationship exists between them. The result of the ANOVA formula is called as the F statistic or F ratio, allows the analysis of multiple groups of data to determine the variability between samples and within the samples. So this test particularly was developed by Sir Ronald A. Fisher around the 20th century. So the t-test and z-test, like we had in hypothesis testing, we have t-test and z-test methods which were developed in the earlier 20th century, which were used for statistical analysis. And later on, like Ronald Fisher created this analysis of variance method. So this ANOVA is also called as the Fisher analysis of variance, and it is the extension of T and Z test. So the term became well known in 1925. This F test, we can call it as F test or ANOVA test. After it appeared in Fisher's book, there is a book called as Statistical Method for Research Workers. So in that he published regarding this ANOVA testing. So basically this is a very famous test like which is out there, and in this test we can basically test more than two groups. Like whenever we want to see like if there is any difference existing between the groups, more than two groups, we can go with this ANOVA test or F test. Now here to take an example, suppose there is a study which is conducted among men of age group 18 to 26 year in a community to assess the effect of SES on BMI. Suppose we have to find out like how SES affects the BMI. So SES is nothing but socio-economic status and how it is affecting the body mass index. Now here we have like three groups of data. We can say lower SES, middle SES and higher SES. So here lower SES values, it shows like socioeconomic status is given by this many years of age, and the number of values and the average within this. So we can see the average of lower SES, middle SES and higher SES is a little bit different. But suppose we want to find out how different they are they significantly different from one another? So in those case we can do this ANOVA test. Now again, ANOVA test is of multiple type. This would be like one-way ANOVA test where we are checking one factor, that is the SES on BMI. Suppose we have multiple factors, then we can go with N-way ANOVA. So to look at one-way ANOVA, like when we are checking effect of SES on BMI, that would be called as one-way ANOVA. The other one is two-way ANOVA test. Suppose we want to test the effect of age as well as SCS on BMI, then it will be two-way ANOVA. Suppose we want to test the effect of age, SCS as well as diet on BMI, then it will be a three-way ANOVA. So similarly, we can have n-way ANOVA based on the number of factors we have, like which we want to test with respect to one outcome or a dependent variable. Now here like first we'll be looking into one-way ANOVA, then we will see two-way ANOVA. We'll just look into some examples in this ANOVA, like how do we do ANOVA testing, like what are the process involved in ANOVA testing. That's what we are going to see. And after that we'll also be doing this ANOVA test in Python. So first to look at one-way ANOVA. So this one-way ANOVA is also called as single factor ANOVA. This one-way ANOVA is called a single factor ANOVA. So this determines mean of greater than equal to three independent groups significantly different from one another or not. So basically, like we have suppose like one group of data, or we have suppose three independent group of data, more than equal to three independent group of data, and we want to see if they are significantly different from one another or not, then we can go with this one-way ANOVA. So here in this one way ANOVA, we'll be having one independent variable. Independent variable will be one. Like that independent variable might be a group variable or factor variable. So we can also call it as a categorical variable. Suppose our independent variable is a categorical variable with more than or equal to three levels, like three different categories. Then we can do one way ANOVA. So here grouping variable, that is the independent variable, should be nominal, and the outcome variable should be interval or ratio. Outcome variable is nothing but to which we want to test the effect. That is, suppose if we take the previous example of effect of SES on BMI, so SES is nothing but it is suppose nominal. So we have three SES values: lower SES, middle SES, and higher SES. And this BMI is nothing but we are testing the effect on BMI. So this BMI would be our outcome variable. So grouping variable would be SES and outcome variable would be the BMI. So this would be one way ANOVA. So while we do ANOVA testing, there are certain assumptions which we take. Like first one is normality, then homogeneity of variances, then independence of error. So normality says the values in each group are normally distributed. So if we take multiple groups of data, so each of the group values should be normally distributed. That's what we assume. The other one is homogeneity of variances. So that is like variance within each of the individual group should be equal for all the groups. So if you take variance of each of the individual group, the variance should be equal to the variance of all the groups taken together. The other one is independence of error. That is, the error should be independent for each value. Error is nothing but the variation of each value around its own group mean. So that should be independent for each of the value. So these are the three assumptions which we take in ANOVA testing. Now we'll be looking into the steps involved to carry out this ANOVA test. So first thing is we have to state the null and alternate hypothesis in ANOVA testing. Then we have to state the level of significance. Then we have to calculate the degree of freedom. Then we have to state the decision rule, and then we have to calculate this test statistic. So first is stating the null and alternate hypothesis. So in ANOVA testing, null hypothesis says that all sample means are equal. Suppose we are taking all the group of data, like suppose we have three groups. We are finding out the mean of each of the three group. By default, null hypothesis says that they are very much equal. So all sample means are equal. So that would be mu1 equals mu2 equals mu3 equals till mu I. I is nothing but number of groups or number of samples we have. So null hypothesis says all the sample means are equal. Alternate hypothesis would be not all of the mu I are equal. That is, at least one sample mean is different. At least one sample has a different mean. So that would be the alternate hypothesis. So this is what null and alternate hypothesis would be in case of ANOVA test. So this is one way ANOVA test. The other one is state alpha, that is nothing but the significance level. So we have to set one alpha label. So alpha level should be like it can be 0.05 by default. Alpha can be 0.05 by default. We can also change it based on the type of test we are doing. Alpha also might change. So here we can start off with level of significance at 0.05. So 0.05 level of significance means the confidence level is 95%. Then the other one is calculate degree of freedom. So we have to find out degree of freedom here, that is given by k minus 1 and n minus 1, where k is nothing but number of samples and n is nothing but total number of observations. So this is where this is how we will be finding out the degree of freedom. After that we have to do the test statistic based on the decision rule. So decision rule would be if calculated value of f. So once we do this test statistic, that is nothing but finding out the f statistic value. So that value is would be called as calculated value of f. So if that value is greater than the table value of f, table value we will get through the f distribution table. So that would be called as critical value. So if our calculated value is greater than the critical value, then we will reject the null hypothesis. So we have to compare the f ratio with the tabulated value of f, and based on that we'll be rejecting the null hypothesis if our calculated value is greater than the table value of f. So now here to calculate this test statistic, we have to find out the variance. First, we have to find out the variance. So here basically we have to find out two types of variance. One is mean sum of square between samples. The other one is mean sum of square within samples. So we have to find out two things here. Now mean sum of square between sample is given by this formula, that is sum of square between divided by k minus 1. Sum of square between divided by k minus 1. So here sum of square is nothing but like this formula is very similar to the variance formula. So we have already seen variance is nothing but x minus x mean whole square, summation of x minus x mean whole square divided by n minus 1. So similar formula is there, that is SSB, that is the sum of square of b, that is sum of square between divided by k minus 1, where k is nothing but number of samples. So this between group means, suppose we have three groups three groups. Suppose we take the SES example, in that we had three groups. Lower SES is one group, middle SES is one group, higher SES is one more group. So the mean of square between would be the variance between each of these. Like if we take each of these together, that is lower SES, middle SES and higher SES, what is the variability among all of this? That will be between group variance. And within group would be like if we take only lower SES, what is the variability within this? If we take middle SES, what is the variance within middle SES? If we take higher SES, what is the variance within that? So that will be within group variance. So between group would be like when we take all these groups and we try to find out between the group what is the variance, that will be between group variance, which is given by MSB, that is mean sum of square between. The formula for mean sum of square between is sum of square between divided by k minus 1, and mean sum of square within formula is sum of square within divided by n minus k, that is n is nothing but total number of observations. So once we find out the mean sum of square between and mean sum of square within, we can take the ratio of both of this to find out the F statistic value or the F ratio. So F ratio is given by variability between group divided by variability within group, that is MSB divided by MSW. So once we calculate this value of F statistic, we have to compare the F statistic value with the critical value, which is obtained by looking in the F distribution table against the degree of freedom as well as the level of significance. So the calculated value of F, suppose the calculated value of F is greater than the tabulated value, then we will reject the null hypothesis. So now here there are two examples, like suppose we have higher variability between group and lower variability within group, like this is lower variability. So what will happen? So here we can see the first case, suppose between group variance is large. So here we can see between group variance is large, like if we take all of these groups or sample data, the variability is large among each of the, like if we take them together, that is between group variance. So between group variance is large relative to the within group variance. So we see within group variance is small. So within each of the group, the variability or variance is small, but between group variance is large. So here F statistic will be larger. In this case, we will get a larger F statistic value, and it will be greater than the critical value. So we can say that there is statistically significant difference. So at least one of the group mean is significantly different from the other group mean. That's what we can conclude in this kind of scenario. The other case would be like within group variance is larger. Suppose we see that each of the individual group variance is larger, that is within group variance is larger, and the between group variance is smaller. So in this case, F value will be smaller. So this will reflect the likelihood of no significant difference between the three sample means, like these three sample means. So here to test this out, like first to look at this table. So this is called as one-way ANOVA table. So first we saw like we have to find out sum of square, like we have to find out sum of square between, sum of square within. Then total sum of square will be addition of both, that is sum of square between and within. Then a degree of freedom would be k minus 1 and n minus k, total is like n minus k. And then we have to find out the mean square variance, that is MSB, which is given by sum of square of between divided by k minus 1, and mean square within, sum of square of within divided by n minus k. Once we find this out, then we can find out the F ratio, which is given by mean of square of between divided by mean of square of within. The ratio of that would be the F ratio. So this is how like the ANOVA testing is done. So first, like we'll be taking one example here to understand ANOVA with respect to a particular example. So suppose here we have three samples obtained from normal populations with equal variance. So suppose we have some sample data, that is like three groups are there, and we have got these three sample data from some normal population distribution which is having some equal variances. Now here we have to test the hypothesis that sample means are equal. So by default null hypothesis says that sample means are equal. Like if we take x1, x2, x3, three samples, mean would be very much equal. So that's what it says. So there is no significant difference among the means. So now to test this hypothesis if there is any difference or not, first thing is like we'll be taking the null. Null says no significant difference in the mean of three samples, it is equal. Then the next here we can take alpha as 0.05, that is the level of significance. Then we can take degree of freedom, that is k minus 1 and n minus 1. So k minus 1 would be 2. So as we have three groups, three samples, that is 3 minus 1 is 2, and n minus 1. N minus 1 is nothing but number of observations minus 1. So that is 12. So we have total of here uh, like how many observations are there, based on that we have to take. So basically this is nothing but this is coming as 12. Now here we have got the degrees of freedom. The next is we will be setting our decision rule. Decision rule says the tabulated value or table value, that is the critical value of f at 5% level of significance. So we have to find out what is the critical value of f from the table. So we are taking 5% 5% level of significance, and degree of freedom we got 2 and 12. So if we look at the F distribution table, so as we are doing an F test, we have to look into F distribution table. So if we look at F distribution table uh, for the degree of freedom 2 and 12 and level of significance as 0.05, the table F value, that is the critical value, is 3.88. So if our calculated value of f is greater than 3.88, then we will reject the null hypothesis. Otherwise, we will not reject. Now we will find out our f ratio or f statistic value. So to calculate the test statistic value, first here like I am calculating the grand mean. So grand mean is nothing but that is given as like x1 mean. Suppose I'll find out the mean of x1, then mean of x2, then mean of x3. So here mean of x1 is 10, that is we have to find out individual mean, that is mean of x1 would be 8 plus 10 plus 7 plus 14 plus 11 divided by 5, total 5 records are there. So that would come as 10, and x2 mean is 8 and x3 mean is 12. Now grand mean is nothing but the total mean, like if we add it all up. So what is the grand mean? So if you take all of them together, so grand mean is coming as 10 plus 8 plus 12 divided by 3, which is nothing but 10. Then we have to find out the sum of square. Sum of square, we have to find out two things, that is sum of square of between and sum of square of within. Now sum of square of between would be n1, that is number of data in sample 1, multiplied by m1, that is mean, sample mean 1, minus grand mean whole square, plus n2, then m2 minus grand mean whole square, then n3 multiplied with m3 minus grand mean whole square. So here we are taking those values, like 5 is the number of sample size, that is the number of observation within the sample 1. Then 10 is the mean of sample 1 minus the grand mean whole square. Similarly, n2 is 5, then m2 is 8 minus 10 whole square, then 5 into 12 minus 10 whole square. So it is coming as 40. So we got a sum of square between as 40. Then we'll be finding out the mean sum of square between. So that would be SSB divided by k minus 1. So that is 40 divided by k is 3, and 1 minus 1, that is 2. So we are getting here as 20. Then we have to find out sum of square of within. Sum of square of within is given by this formula, that is summation of x minus uh, mean, that is mean of each of the value, that is x minus x mean whole square plus x2 minus x2 mean whole square, like that. So here we are getting the value as 30 plus 16 plus 14 equal to 60. Then mean of square within will be sum of square within divided by n minus k, so it is coming as 5. So we got mean of square between and mean of square within. So now F ratio is nothing but mean of square between by mean of square within, that is 20 by 5 equal to 4. So here we are getting F statistic value as 4. So now here the tabulated value was 3.88 and our F value is 4. So F value which we calculated, that is the calculated F statistic value, is higher than the table value. So that's why like null hypothesis would be rejected. So as our calculated value is higher than the critical value, null hypothesis would be rejected. So hence we can say there is significant difference in sample mean. So there is some significant difference in sample mean. So this is what we will conclude from the test. So this is how this one-way ANOVA testing is done. Now if we go with two-way ANOVA. So two-way ANOVA is when two independent variables, nominal as well as categorical, have an effect on one dependent variable, ordinal or ratio measurement scale. A dependent variable will be in ordinal or ratio measurement scale. So then we can do that test in two-way ANOVA. So if we have two independent variables which we have to test with respect to one dependent variable, we can go with two-way ANOVA. So here two-way ANOVA compares relative influence on dependent variable, like how the independent variables are affecting the dependent variable. It examines the interaction between independent variables also. So just as we had sum of square and mean squares in one-way ANOVA, we have this same in two-way ANOVA also. Now this includes three null hypotheses. This will have three null hypotheses. As we have like two independent factors here, it will be having three null hypotheses. So first one is mean of observation grouped by one factor are same. First null hypothesis says mean of observation grouped by one factor, that is one independent variable, is same. Then mean of observation grouped by the other factor are same, that is the second factor is same. And the third one is there is no interaction between the two factors, that is the interaction test tells whether the effect of one factor depend on the other factor or not. To take an example and understand, so suppose we have a test score of boys and girls in age group of 10 year, 11 year and 12 year. So if we want to study the effect of gender as well as age on score, suppose we have two factors here, gender and age, and these are two independent factors and score is our dependent factor here. So two independent factor we have, gender and age, dependent factor is test score. So here we will be having three null hypotheses, that is H naught, which says gender will have no significant effect on student score. Then the second null hypothesis will be age will have no significant effect on student score. Third null hypothesis will be gender and age interaction will have no significant effect on student score. So here we have three null hypotheses. So we'll be doing this we'll be doing this one-way ANOVA as well as two-way ANOVA in this one Python, to see like how it's implemented in Python. Now to look at two-way ANOVA table, so here it's very similar, like we have two factors instead of one factor here. So that's why we have to find out degree of freedom here also for factor A, then for factor B, then the interaction, it is nothing but like when we take factor A and B together, and the error, that is the within factor variance, the degree of freedom. Then sum of square, we have to find out sum of square similarly, then mean of square, then we have to find out the F ratio, then we will be finding out the p value and we'll compare the p value with the significance level, and then we will decide should we reject or not the null hypothesis. So we'll test this out in Python. We'll just see how to implement this thing in Python. So here we'll be doing a ANOVA test, like we'll be using Python, and we'll see how to do ANOVA testing using Python. So now here first thing is like I'll be importing certain files, that is I'll say matplotlib inline, will import numpy and pandas. So we'll be using numpy, pandas, matplotlib as usual, And here we'll be using this data set, uh, read underscore CSV. So here there is a CSV file under datasets folder. This file is plant growth. So now in this data we have 30 records and 3 columns. If you look at data.head, it shows all the data like what are there, like top 5 records. So here we can see we have something called as unnamed, one column unnamed, and the other column is weight and the other column is group. So this data set is plant growth.csv file. So now in this data set we have basically 3 columns. One is just the serial number, that is unnamed, and 2 columns, 2 main attributes are there, that is weight and group. Now the main job here, what we are trying to do is we have weight. So weight actually tells what is the dry weight of plant. Okay, weight is just a factor which tells us about the growth of plant, like if a plant has grown or not. That is like what is the weight of the plant, that is the dry weight of plant. And group is nothing but it shows us different type of treatments here. Like to see the unique values, we can just see what are the unique values here. So I'll say pd.unique of data group, column name is group. So here it shows there are 3 unique values, that is like 3 classes or 3 levels of category. One is CTRL, TRT1, TRT2. Now within this data it shows like different treatments. These are nothing but treatments, and this weight is nothing but the dry weight of plant. So this data shows us what are the dry weight of plant based on the different type of treatments. So based on control treatment, like when a control treatment is given, what type of weights are there. When a treatment 1, when some kind of treatment like treatment name is treatment 1 is given, what is the weight of plant, and treatment 2, what is the weight of plants. So dry weights of plants. So that's what here it shows. Now suppose here, suppose we have to find out if there is any if there is any difference, significant difference between the treatments. Like when we are giving these different types of treatment, is it affecting the plant in a different way or not? So here basically we are just going to see if there is any difference within these treatments. Now here treatment, that is the group, is nothing but categorical column, and the weight, that is our outcome, that is the target value here, dependent variable, is a numeric column. So now here we just want to find out if there is any difference within the group means. So here in this ANOVA test, we'll do an ANOVA test to find out if there is any difference within the group means. Now here we have 3 groups, so we can just divide the data into 3 parts, saying what are the weights of plant when control treatment is applied, what are the weight of plant when TRT1 is applied, similarly what are the weight of plant when TRT2 is applied. So we can just group it, then we can check what are the mean, what are the average of each of the group, then we can just see if there is any difference within the average. So for this kind of test we can do one way ANOVA, as we are checking one factor, one group factor, that is one factor with respect to weight. So we can do here one way ANOVA test. Now here first to see if there is any difference within the group center values, like what we can do is like we'll just plot it in a box plot, uh, just to observe the data, just to see how the data is distributed. So I'll take here weight and group, and I'll also give a figure size so that we get a big size figure. Figure size equals, I'll give you 12,8 suppose. Now here it shows a box plot, it shows different groups in x-axis, those are the different types of treatment. And when you can see here on the x-axis it says CTRL, TRT1, TRT2. So when CTRL treatment was applied to the plant, then what was the weights, what are the different weights? So we can see here, this is the minimum weight, this is the maximum weight, and this is nothing but the IQR. Similarly, what are the weights for treatment 1, what are the weights for treatment 2? So we can see there is a difference within the medians also, like the center values. There is some difference within the within these treatments. But suppose we want to see how significant different they are, like significantly are they different or not. So for that we'll be doing ANOVA test. So for doing ANOVA test, we have to first extract this data. That is for CTRL, what are the different weight values, for TRT1, what are the weight values, then for TRT2, what are the weight values. Then we can compare those weight values to see if the weight values are different or not. If the average values of weight for each of the treatment is significantly different, then we can say that these treatments vary from one another. They contribute or they affect the weight of plant in different ways. So they are significantly different is what we can say if we observe, like if we get to see different kind of variance. Now here for that, first we'll be extracting the data. So I'll just write a for loop here, a single line for loop I'll write. So I'll take the unique value. So I'll say unique unique of we'll be taking group data. So data dot group, and I'll be taking it in array format here. So pd dot unique of data dot group dot value. So this will have all the group values like CTRL, TRT1, TRT2 in array format. And here I'll just write a for loop. So here I'll say a for loop. So we'll be converting the data into dictionary. So here I'm giving curly brackets. So within the dictionary we'll be passing the key, and we'll be getting the data of weight. So we need weight for each of the individual keys. So for that we'll be writing a for loop. So I'll say for I in GRPS. So GRPS is nothing but CTRL, TRT1, TRT2, and we'll say if, so here we'll write one more condition, if data dot group value is equal to I, then give us I colon data dot weight. So what this will do, this will give us data in this format, that is d underscore data. We can see here CTRL, it shows all the weight values for CTRL, and the next one is TRT1 or all the weight values for TRT1, like that. So now if I say d underscore data of CTRL, it will only show me the series of data for CTRL. Similarly, if I say d underscore data of TRT1, it will show me the values for TRT1. Similarly for TRT2, d underscore data of treatment 2. So these are nothing but it shows the corresponding weight values for each of the treatments. So now we have three data. Now we have three groups of data: CTRL, TRT1 and TRT2. So we have three samples now. Now we will be looking at this one, that is how different are these sample data, that is that will tell us like how these weights are varying from one another or are they same. So that's what we'll get to know here. So first to do this test, here in Python we can use a package that is SciPy. We can use SciPy, scientific Python. In that there is something called as stats package. So we'll use scientific Python stats package. So for all statistical calculation, this is the package we can use. And within this we'll be using this function, that is stats dot f underscore one way. So to do one way ANOVA, there is this function f underscore one way, through which we can do one way ANOVA. And this function will return two things: one is f value, the other one is p value. If the p value will be less than the significance value, that is suppose 0.05, then we will reject the null hypothesis. If p value will be greater than significance value, we will not reject the null hypothesis. So here null hypothesis says that there is no difference among the group means, that is like if we take this group data, that is CTRL, TRT1, TRT2. So null hypothesis says that the mean of CTRL data, the weights with respect to CTRL, mean of weights with respect to TRT1 and mean of weights with respect to TRT2 are very same. So there is no difference, like they are very same. So we have to see if they are significantly same or significantly different. So for that, here we'll be passing those three data. So I'll be passing here d underscore data of CTRL. So we have to pass all the samples here, d underscore data of TRT1 and d underscore data of TRT2. So we are passing three samples, and from this like we'll be getting the f value and p value. So now f value here is 4.8640, that is the f value, and p value, that is the probability value, is 0.015. So we can see here the p-value is less than the significance value. Suppose we are setting the significance value as 0.05. This p-value is less than significance value. So as p-value is less than significance value, we can reject the null hypothesis. Null hypothesis says that there is no there is no significant difference among the means. Mean are equal for each of the group, but we can say there is some significant difference. So we can see there is some significant difference within the group mean, that is the treatment which are given to the plant, like applied to the plant, CTRL, TRT1, TRT2, are affecting the plant growth in different ways. So they are significantly different from one another. That's what we can conclude. So this is how we can do one way ANOVA. So here I'll just write it down, just a mark down saying. So this is one way ANOVA. Now we will do a two-way ANOVA. So we'll take one more data set and we'll try out with two-way ANOVA. So now for working out with two-way ANOVA, we'll be using a different data set here. And this data set is nothing but we'll be using a tooth growth data set. So I'll just explain you about the data here. pd dot read underscore csv. So I'll just name it a different data, saying data. I'll just name it as df. So now within this data we have 60 records and 4 columns. Now if you look at the head of the data, it shows there is a column called as unnamed, and there is something called as length. LEN is length, and SUPP is supplement, and DOSE is dose. So here we have this 3 records, actually 3 different columns here. Unnamed is nothing but the serial number, and length column tells us about the length of teeth of guinea pigs. Now this is a data with respect to guinea pigs. So this is a research data, like some of the scientists or researchers, they gave different supplements to guinea pigs, and they wanted to see if these supplements are different from one another, like each of the supplements are contributing to the length of teeth in different way or not. So these supplements are meant to increase the length of the teeth of guinea pig. So like once they have given all these supplements, so we'll see like what all supplements they have given. So here basically we have 3 unique values. So pd dot unique we can say, and df dot supplement. So there are 3 types of supplement, 2 types of supplement which are there. One is VC, the other one is OJ. Now the researchers, they gave different supplements to guinea pigs. One is VC supplement, one is OJ supplement to guinea pigs, and they recorded the length of teeth with respect to each of the supplement. Now whenever like supplement is given to a guinea pig, that supplement will come up with some dose. Like whenever like we get some medicine from the market, we have to get it with respect to some dose. So we cannot say like, you can also say like medicines of different doses will affect in different ways. So that's where, like here one more factor is there, that is dose. So if you look at the unique values within that, this is also a categorical column, so we can just look into dose. So here we can see 0.5 dose, 1.0 dose, and 2.0 dose is given. So there are three doses with respect to each of the supplement. So VC supplement was given with 0.5 dose to certain guinea pigs, and the length of teeth was recorded. Similarly, a VC supplement with 1.0 dose and VC supplement with 2.0 dose was given to some of the guinea pigs. Now similarly, OJ is also given with the respective doses 0.5, 1 and 2. Now here suppose we have to find out uh, with supplement and dose, if you take supplement and dose together, how it is affecting the length of teeth. So we have to see how supplement independently is affecting to the length of teeth, how dose independently is affecting to the length of teeth, how supplement and dose interactively is affecting to the length of teeth. So here we have 3 null hypotheses. Like here we'll be getting 3 test values. So we have to do 3 F tests here. So now to do F test here, first thing is, like we'll just see if there is any difference or not. So I'll just draw a figure. So we can do a factor plot here. Now to do factor plot in matplotlib, there are not much greater factor plot, so we can use this stats models package. In stats model graphics, so stats models, there is a package called as graphics, and in that there is something called as factor plots. Now there is a factor plot called as interaction plot. We can use this interaction plot from stats model. So just to do a factor plot, as we have two factors here, that is supplement and dose, and suppose we want to see, okay, how supplement and dose are contributing to the length of teeth, the average of length of teeth. So we can do a factor plot here. So I'll just do a factor plot saying interaction plot, and we'll be passing the data. So data is, one is dose, we'll take it in x-axis, and data dot supplement, we'll group it by supplement. So first one is the x value, then the group value, we'll be grouping it by supplement, and then y value is nothing but length, teeth length. So this len column is nothing but, it tells you what is the length of teeth of guinea pig, so when a particular supplement is given. Then we'll take some colors here, we'll just add some colors to the graph, red and blue, and some markers. D means diagonal, and we'll also use cap. So this is nothing but triangle. And what should be the marker size? So we can also specify the marker size here. It says data frame has no attribute SUPP. Okay, sorry, here it should be DF. It should be DF. This should be DF. So now this is what graph it shows. It shows three different markers. We have given marker size is 10. So if you give a higher size, bigger size, it will be big in size. So here it shows the dose values, like what are the different dose values. We have three dose values, 0.5, and the other one is 1.0 and 2.0. So when these different type of doses are given with respect to supplements, like red one is OJ supplement and this blue one is VC supplement. So what are the different average length of teeth of guinea pigs? So here we can see, like when 0.5 supplement 0.5 dose was given for supplement VC, the length, average length is somewhere around 7.5, and when OJ supplement is given with a dose of 0.5, it is somewhere around 12.5 or 13.0, like that. So here we can say that they are significantly different, like it looks like they are significantly different. The average of length of teeth for each of the supplement with respect to dose is significantly different. Similarly for the second one also we see they are significantly different, but at third one we can see that they are very same. Like at the third stage it shows like both of them are contributing to the length of teeth in the same way. So now here there is a confusion, like if overall it is significantly different or not. So for finding out that, we can do this two-way ANOVA. So here why we are doing two-way ANOVA? Because we have two factors combined together, which is going to be used to check the effects on the length of teeth. So now for doing this two-way ANOVA here, we'll be using this package that is from this table we can use. There is a package in OLS. There is something called as OLS test. We can use that package to do this two-way ANOVA test. So we'll just do the two-way ANOVA test here. So we'll be using that stats models. In stats model, there is something called as API. So we'll be importing from that API. There is something called as SM, and we can also import OLS. So from, I'll say here import stats models dot formula dot API import OLS. Sorry, dot OLS. So we have imported SM and OLS here. So first thing is like this is nothing but stats model package. So there is something called as API. We can use this package to do ANOVA test. Now to do ANOVA test, we have to first specify like what all things we want to pass. So we want to test the effect of supplement and dose with respect to length of teeth. So we'll be passing length as our output factor. So this is our output factor, and here uh, we have to test this output factor, that is length, with respect to supplement and dose. So here we will say supplement and dose are our cofactors, that is dose, and the other one is supplement. So we have to just multiply like this. So this is the syntax here, and we have to say which data is that. So we'll say df is the data set, and then dot fit for training the model. So dot fit, then here result will be sm dot stats dot ANOVA lm, and we'll pass this model, and type is nothing but 2. So this is how like we can do a 2-way ANOVA test. So here once we do this, so here we are just passing the data saying alien the length. We are checking the dose and supplement, like how dose and supplement are affecting with respect to the length of teeth. And here like once we do the test, it shows what are the sum of square value for dose, what is the degree of freedom for dose, and what is the f ratio for dose, that is the f statistic value. Similarly here it shows what is the supplements sum of square value, df value, degree of freedom, and f value, and c, and that is dose as well as supplement. So interaction of both dose and supplement, what is the sum of square, degree of freedom, and f value. So here we can see the p value, which is coming as 2.186027 e minus 02. So here this is a very small value, so which is less than 0.05. So here as the supplement and dose values both are less than 0.05, if we take the interaction of both, so they show a significant difference. So when we take both of them together, we can say they contribute to the length of teeth of guinea pig in different ways. So each of these supplements with respect to dose are very different from one another, are significantly different from one another, that's what we can say. Similarly here it shows for dose only, like for dose, like if you take dose only, it says okay, dose also the average values or the mean is very different. For supplement also it's very different. So we can say that they are very much different. So as the value is less than 0.05, that is our significance value, we can reject the null hypothesis. If p value is less than alpha, that is the significance value, we can reject the null hypothesis. So that's what we can do here. We can reject the null hypothesis, saying that saying that there is some significant difference. Okay, by default null hypothesis there is no significant difference within the group means, but we can say there is some significant difference as the p value is less than the alpha value. So this is how we can do a two-way ANOVA test also. So it's very simple, very easy, like we can just use stats model package to do that. And for doing one-way ANOVA, we can use SciPy stats package to do one-way ANOVA. So this is all about ANOVA testing. So here basically like what we have done is we saw what is one-way ANOVA, two-way ANOVA. Similarly, there can be n-way ANOVA. So if there are multiple factors we are taking into consideration, then there can be n-way ANOVA also. So here we'll keep it till this for ANOVA testing. Thank you.